greetings from Hawaii. Sorry I can't be there in class today, but you're in good hands with Jen Sparks. Please treat her as kindly as you treat me. And also please feel free to ask her questions just as you would ask me questions. She is here to help you out just as I am there to help you out on normal occasions. So the plan for today, you've already had the quiz, I hope. And so I'm going to go over the answers to the quiz. Then I'll spend a little bit more time just reviewing what we covered last class. And then we are going to start our next segment, which is on minerals. So as I go over this quiz, right, you can self-grade yourself. You should still have this piece of paper in front of you. So hopefully you've marked on your quiz what answer you put. I'm now going to go over the correct answer. So yeah, by the end of this, you should know what grade you got on today's quiz. So the first question, how old is Earth? You should hopefully have said Earth is what? Is it 3.2 or 4.5? Well, yeah, it's 4.5. Is it 4.5 million, billion, or trillion years old? It's 4.5 billion years old, this one right here. So you should have put C for your answer to question number 1. Question number 2, which of Earth's layers contain the most silicon and oxygen? This actually went back to last week when we were talking about differentiation. So that layer that contains the most silicon and oxygen, hopefully you put the Earth's crust. Those are the lighter elements. They floated to the surface. Question number 3, what is the MOHO? It is the boundary between the crust and the mantle. This is where seismically we're seeing that change in seismic speeds from that crust layer to that mantle layer below. That boundary we call the MOHO. So if I drew a picture like this on the board, well, first off, let's just make sure we know what the various letters are. So what would the letter A refer to? If you said the core, you're close. What's more specifically A? The inner core, so that's the inner core. What is B? The outer core. This line marking the boundary between the mantle, which is C, and the core, it doesn't have a name as far as I'm aware. It's this line right here marking the boundary between the crust, which is W and X, and the mantle, which is C. That line, that is the MOHO. And I know there's a quiz question on it a little bit later on, but if you're comparing X and W, those are two different types of crust. What is the X? It's continental crust. And how should you hopefully recognize that it was continental crust? It's thicker, right? Continental crust is thick, oceanic crust is thinner. So the X is continental crust, the W is oceanic crust, I should say the C is the mantle. The line between C and the W and the X, that is the MOHO. That line right there marks the boundary between the mantle and the core. B is the outer part of the core. A is the inner part of the core. So then we were talking about, well, how do we know how big the core is? And that's what question number 4 is talking about. What would it mean if Earth's seismic shadow zone was larger? If that area of shadow, the area not receiving S waves, was larger, would that mean that the core was larger or that the core was smaller? Should be larger. If the core is larger, it's going to be blocking more of those seismic waves. It's going to cause a shadow to be larger on the other side. And here's just that picture from last class. So this is today's size of the core. But if the core was larger out here, right, this wave over here and this wave over here wouldn't make it to Earth's surface. It would go into the core and never come out again. And similarly, those two waves on the other side, they also would go in and they wouldn't come out. So the area in shadow would be bigger if the core were bigger. Next question, question number 5. Where do geologists think Earth's magnetic field comes from? Does it come from penguins? Yeah, hopefully you didn't put penguins. Does it come from cosmic radiation from space? Yeah, no, space is not making our magnetic field. It's not frictional drag. It's not because of bonds between silicon and oxygen. It's due to the movement of iron in Earth's core. So the answer to number 5 was C. Question number 6, which most accurately describes Earth's magnetic field? Does it remain stationary through time, with north always pointing to north? Or has it changed locations through time? Sometimes magnetic north reverses and ends up being pointed where magnetic south is located. So stationary, or does it change locations through time? It changes locations through time. So the answer was B. So we talked about those magnetic reversals that were happening. Right, so this was that computer simulation that geophysicists did where they modeled the Earth and then just kind of let it run, right? We're talking about how the liquid in that outer core can reverse directions, and that would cause the magnetic field to reverse, and we can see evidence of that here. We also looked at the pattern of reversals through time. We talked about how those reversals act kind of like barcodes, so we can use them to determine what the various age of the oceanic crust or the age of the Earth at various points in Earth's history based on this pattern of reversals. So again, the answer to number 6 was B. Earth's magnetic field changes locations through time. It reverses through time. Question at number 7, how does oceanic crust compare with continental crust? And we were just going over that with a picture, right? Continental crust is thicker, oceanic crust is thinner. But this question has 2 parts to it. There's the thickness question, and then what is it made out of? Are they the same rock, or are they different types of rock? They're made out of different types of rock. So B was the correct answer to this question. Continental crust is thicker than oceanic crust, and they're also made out of different types of rocks, right? You don't necessarily know what these rocks really are. I mean, we talked about how oceanic crust is basalt. Continental crust is overall granite. We'll define those rocks. You'll learn more what they are a little bit later on, but they're 2 different types of rocks. We also talked about how they have different densities. How that continental crust, that granite, is less dense and therefore is floating up higher. The oceanic crust is more dense and therefore sinks down lower, which is why water is collecting over it. It's just kind of lower down than the continental crust. And then question number 8, regardless of whether they are passing through the crust, the mantle, or core, seismic waves always travel the same speed. That is false actually for a couple of reasons. What I was hoping you would be thinking about is that we know the difference between the crust and the mantle. We know the MOHO exists because the seismic speeds change. Some of you might also have noticed I talked about seismic waves traveling through the core. And yeah, those S waves, they can't travel through that liquid outer core. So you might have picked up on that. But my point is that the seismic waves, their speeds tell us what they're traveling through. Their speeds change depending on what they're traveling through. Question number 9, we know that Earth's core is made out of a very dense material, but there is no way of knowing whether it is made out of iron or something else dense like lead. Now, we're talking about several reasons why we think the Earth's core is made out of iron. If all we were looking at was the weight of the Earth, then yeah, all we know is that the core is made out of something that's really dense. And yeah, if that was our only piece of evidence, then maybe it could be something like lead. But what's that? What was that referring to? That's a meteorite. So we talked about how debris from space contains a lot of iron, and so that was one really good reason to think maybe the core is made out of a lot of iron. What's the kind of biggest, most important thing? What's the main reason that we know the Earth's core is made mostly out of iron? It's because Earth has because it has a magnetic field, right? We talked about how electromagnets work, and really that iron is really the best material for creating a magnetic field. And we know that, again, that movement in the outer core would cause all of the little electrons, all that iron to spin in the same direction, creating a magnetic field. And you really need a big chunk of iron in order for that to work. And then finally, we talked about roots, talked about isostasy, this idea that those continents are kind of floating in the mantle. And I know the mantle is not liquid, but if you kind of imagine it kind of floating there like a marshmallow in a cup of hot chocolate, the idea is there's that part that extends beneath, that's that root. And we talked about if you add more to it, if you make that mountain or continent taller, it would sink into the Earth. And so question number 10, it says the taller a mountain or continent is, the deeper a root it will have. That is true. So again, here's those models of the roots, whether you like the marshmallow model or the tooth model or the kind of classic iceberg model, right? There's that part that's underneath. There's the the part of the continent you see, the part of the continent that you don't see, and the higher up it goes, the further down it extends. And that's actually what these series of pictures, I think I showed you all, but this is what I'm covering up with my head right now. So if you put blocks of wood, a bigger block of wood floats higher, it extends down different. This is, to me, I think one of the best images of that. This picture I didn't actually quite show you guys last class, but it's showing you the progression of how Earth's continents will change size. So as erosion removes the outer skin of the mountain, there's less holding that whole continent down. It rises up, creating a less and less deep root. So again, tall mountains, deep roots; less tall mountains, less deep roots. And then the other thing we talked about is if you, again, add weight to it, if you add more material, it will cause it to sink down and get a deeper root. If you remove material, it'll cause it to rise up. Again, you can maybe imagine like a pool toy, same idea. You add, material. Somebody climbs onto the little pool toy, or actually I was paddleboarding. You climb onto a paddleboard, it sinks down. You get off of it, it bobs back up again. Okay, so we finished our description of the Earth, how it formed, how it differentiated, all those different layers. And then as we were talking about in lab last class, we were talking about how as the crust and mantle solidified, the solid parts of the Earth, those are rocks and minerals. But I didn't differentiate between rocks and minerals. I know we did a lab where we talked about some physical properties that minerals have, but we still haven't really talked about what makes something a mineral compared to a rock. So what's the difference between rocks and minerals? So that is where we're going to go next. You're going to see, I will have already written it on the board, this kind of what is the difference between rocks and minerals. So here's where you want to make sure you start taking notes. And this picture right here might help us start to think about, okay, which one of those things is a rock and which one of those things is a mineral. But I'm going to walk you through that in this video. So make sure you put that heading, and let's start talking about some new lecture material. What's the difference between rocks and minerals? So how minerals differ from rocks. So what I like to do is actually just pull up a bunch of samples, and then I usually kind of line them up on the desk. Can't really do that very easily here, but I'll hold as many in my hand as I can. So let's see if how your intuition is, and it's okay if it's not right. So here is a sample right here. Ooh, pretty. Can you see that there's like pink areas? Actually, it kind of matches my shirt now that I'm looking at it. Some pink areas, some black areas, some white areas. It's kind of speckled like that. So is this a pretty speckled rock? Or is this a pretty speckled mineral? Is this a rock or is this a mineral? Okay, let me grab this one. So this one right here, shiny, sparkly pink. Is that a shiny, sparkly pink rock? Or is that a shiny, sparkly, it's maybe not that shiny, but anyways, is this a pink rock or is it a pink mineral? Do they look the same? Are they both rocks? Are they both minerals? Is one a rock, one a mineral? Let me grab another sample. I need another arm. Let's do this one. So I don't know. Let's see if we can see what these things are. So maybe like on this bottom other corner, this corner over here, maybe you can see that little spirally shape, or maybe some of these over here look familiar. They're shells. So you have shells and a background of sand. So is this shelly, sandy thing a shelly, sandy rock? Or is it a shelly, sandy mineral? Not easy to say. Does it look more like the speckledy thing over here? Or does it look more like the pink thing over here? Just wait. Let's see. Ooh, what about this one right here? Oh, actually, let's do this one first. It's a spear. Is this a spear of a rock, or is it a mineral? Does it look more like the speckledy things, or does it look more like that pink thing? I mean, obviously it's not pink, but how does it fit in? What about this one? What about this one? What about, ooh, shiny, sparkly one? What are you thinking about? What's going through your mind when you're asking yourself, is something a rock or is something a mineral? Like if I were to ask you, if I were to give you the samples and you were to put them into two different piles, would you say, what would you use, I guess, as your criteria? And maybe just because I can't hold other samples, I could at least show you these pictures here. So there's that sample. There was one with some shells in it. There was a kind of that one. And then there was one that looked kind of like that. So of those 4 samples, how many would you say are rocks? The answer is 3 out of 4. What do 3 of them have in common that the 4th one doesn't have? And I wish you guys were here because it's really fun to hear like what sorts of things people are observing, because they're great things. I mean, it might not be the answer, but it's cool to be like thinking about like how do people see samples? Because I've been doing this for so long, I'm trained to see certain things, but without the training, you might see different things, and those different things might be super valuable. So I wish I could hear you. Oh well. So let me show you the pink one. I wonder if I can force it in the bottom screen here. There we go. So does this look more like the speckledy ones or more like the speary one? Like that description? Notice how this is really one thing. If we go up here in the upper right-hand corner, that's all one thing. And I get there's multiple crystals, right? So partly it's a language thing, but each crystal looks the same. They have basically the same color to them. If we look at the speckledy thing here, if we look at this one, which I'm not sure why I'm holding up since it's there on your screen as well, but there are areas that are pink, areas that are black, areas that are white. And even if you can't tell what those things are, you can tell it's a mixture of different stuff. Shells and sand, again, even if you can't tell that they're shells and sand, it's a mixture of different stuff. This thing, again, even if you don't know what you're seeing, it's a mixture. There's light areas, there's dark areas. This is not a mixture of different stuff. This is one thing. And that's really the key thing to be looking for. If you see a bunch of speckledy different things, even if you can't tell what they are, you're looking at a rock. So rocks are made out of a collection of different stuff, as I like to say. Very technical of me, I know. So maybe make a little chart. Honestly, there's not going to be much in the rock side, so it'll be much more in the mineral side, but. So rocks are made out of a collection of different things, out of different stuff, if you like. Again, rocks are made out of a collection of different things. In the case of this sample, the different things are different. Actually, let me do the sample. Start here. In the case of this one, the different things are like shells and sand. In the case of this thing, the different things are different bits of rock, different pebbles and sand, things like that. And this one, we'll go back to this one finally, this is made of minerals. So minerals can be found in rocks. The mineral is that one little part of it. If you see a collection of different things, you're looking at a rock, not at a mineral. So just some examples of some of these things. They could be shells. They could be sand. Pebbles, minerals. There's all these different things that can be collected together, and that collection is a rock, not a mineral. So to be a mineral, whether you're the pink thing, or this thing, or the spear, or, ooh, let's get this sparkly. I like sparkles. Yeah, even if you can't tell what it is, this is all kind of silver looking throughout. This is all pink throughout, that's all kind of yellowish throughout. So they each are made of basically one kind of thing. So one thing that has to be true to be a mineral, it's not the only thing, but one thing that has to be true, and I'm going to make a list of several things, but the first thing is minerals have a single chemical composition throughout. So again, minerals have a single chemical composition throughout. Sorry if I turned my head away. A single chemical composition throughout. Now I erased my out. Perfect. Okay, so minerals have a single chemical composition throughout. Now that's not to say that they can only be made out of one element. So this is a quartz crystal. Quartz has the chemical formula SiO2. And no, you don't need to memorize the chemical formulas in this class. If you are going to be a geology major, there were a couple of you guys in your surveys that told me you're thinking of being geology majors or you plan on being geology majors, and it makes me very happy. And those of you that aren't, I still love you. It's all good. Just, Anyways. Okay, so for example, quartz. It has the chemical formula SiO2. So all that chemical formula is saying is that for every one atom of Si, which is silicon, there's like an imaginary one. If you don't see a number, the default is that there's one. So for every one atom of silicon, there are 2 atoms of oxygen. So that's my single chemical composition. It's like, whatever, you have a chocolate bar versus a chocolate bars are kind of a theme for my classes. All right, so you have a chocolate bar and a chocolate bar with almonds. The chocolate bar with almonds does not have a single composition. In one area, you'll get chocolate. You hit a different area, you'll get an almond. If it's a straight chocolate bar, then it's a single chocolate composition which doesn't change anywhere in the bar. So it might be a complicated formula, but it's the same formula everywhere. So whether I sample the tip of the crystal, or the side or the front of the crystal, or the side of the crystal, or wherever, anywhere that I sample this crystal, there'll be exactly 1 atom of silicon for every 2 atoms of oxygen. It has a single chemical composition throughout. I don't know that you need another example, but this is another mineral you're going to see in lab. This is the mineral calcite. Calcite has the chemical formula CaCO3. I would have made it the same color, but I left the blue pen over there. Oh, actually it's in my pocket. Oh well. So calcite, CaCO3. So there's 1 atom of calcium, that's what Ca means, 1 atom of carbon, that's what the C is, for 3 atoms of oxygen. And again, you don't need to know the formula. The point is it has a single composition. No matter where I sample, I'm going to always have 1 atom of carbon, 1 atom of calcium for every 3 atoms of oxygen. It's the same composition throughout. And again, if we did this with a rock, we'd get different things. I sample the pink area, I get 1 chemical formula. The black area, a different chemical formula, so on and so forth. So let's actually just kind of look at that here in this next slide. So again, rock or mineral? Rock. It's a rock that's made out of a collection of minerals. So these are the names of the minerals. You will get familiar with all of these minerals. In fact, these are 3 minerals you'll need to know for the mineral exam. And if you're like, how am I supposed to know these minerals? There'll be time. So next week's lab, you'll learn how we identify minerals. And then there'll be a lab the following week where the entire lab will just be spent learning the minerals you'll need to know. And there's 9 minerals that are really common minerals that we find in rocks that really everybody who takes a geology class should know those 9 minerals. So these are 3 out of the 9 minerals, and you'll learn everything you need to know in lab. So don't worry, you'll get there. So I'm not sure why, but what makes something a mineral down there, so just ignore that. So quartz's chemical formula is SiO2. Potassium feldspar, the pink mineral there, has a longer, maybe uglier, in your opinion, chemical formula. The biotite mica has an even fancier chemical formula. The point is not to learn the chemical formulas. The point is that that sample does not have a single chemical composition. It has different ingredients in different areas. So what you're looking at on the screen there is a rock. To be a mineral, it's just one composition throughout the entire sample. Okay, so that's one thing that has to be true to be a mineral, and that's really the main thing that differentiates rocks from minerals. But let's talk even more about minerals because, well, you'll see. So let's say I take that quartz crystal, whatever, it's on the screen, and let's say I heat it up so much that it melts. So that other picture up there, let's just say it's actually water. But let's say it's liquid quartz. Or actually, we could even say water. Water has a single chemical composition, H2O. Is this a mineral? Is that liquefied quartz a mineral? It has a single chemical composition throughout. What does your intuition say? Can minerals be liquid, you think? I'm hoping your intuition says no. So a second requirement to be a mineral is that you have to be solid. So if you start with a solid mineral and you melt it, you'll have liquefied mineral, but it's not technically a mineral anymore. And this can be confusing for students because you've probably heard of mineral water. It's one of my pet peeves because mineral water doesn't contain minerals because minerals are solid. Okay, what they're talking about, so if I'm being charitable to them, so there are minerals which are solid. When you dissolve them in water, you get mineral water. So mineral water contains dissolved minerals, but technically because they're not solid anymore, you shouldn't call them a mineral. So you take some magma, some molten rock, you liquefy it, it might eventually turn into minerals as it solidifies. But as long as it's liquid, it's magma. There's another name we use for it. Magma is kind of the typical word that we would use. You're not a mineral until you're solid. So you both have to be solid and you have to have a single chemical composition throughout. Okay, I'm going to continue being mean. I'm going to hide here in the corner. Glass. Do you know how glass is made? You take sand. You can mine sand. You could go to the beach. Your kind of classic sand is actually made up of ground up quartz crystals. So I take that SiO2. I break it into little pieces. I've got myself sand. I melt the sand. I have liquefied SiO2. Again, if it's liquid, it's not a mineral. But then we take that liquid and we cool it really fast and create this beautifully transparent material, which we call glass. So glass has a single chemical composition throughout, SiO2. Yes, there could be impurities, but let's pretend it's pure SiO2, because that's not the point. So it's SiO2, and it is a solid. So glass is solid. It has a single chemical composition throughout, and yet I'm telling you, it's not a mineral. Why do you think it's not a mineral? I mean, maybe intuitively, you're like, yeah, I wasn't going to call it a mineral. But do you know what else has to be true that makes glass not a mineral? There's actually two things. One is, I think, maybe more important than the other. Let's first talk about maybe the less important one. I'm not sure what logic there is to that. But one thing you might be thinking is, well, okay, if it's man-made, if you're manufacturing something, manufactured minerals aren't minerals. So like cubic zirconia. If you make a mineral in a laboratory, if a human's making it, technically we shouldn't call it a mineral. Some people do, but they shouldn't. Mineraloid is the more appropriate term to use for a mineral-like thing, which is not a mineral because a human made it. So a third thing, and the wording we tend to give it, is it must be naturally occurring. To be a mineral, you must be naturally, that's an N, a little hard to see, but it must be naturally occurring. And I don't know if you're like me, but this has always been a pet peeve of mine. It's like, I was born here on this earth. I am natural. Not in science speak. So science speak, if humans are doing something, it's not natural. We could have a whole philosophical discussion about that if you wanted to. So another word sometimes people use is it can't be man-made. But then I also have issues with that because I'm a woman. So like if I make it, does that mean it's not man-made? And you're like, of course it doesn't mean that. But anyways, the point is, if somebody is making it, you shouldn't call it a mineral. And in the glass that you have in your windows, okay, humans made it. So, okay, that is one reason that glass is not a mineral. It's not the best reason, and here's why I'm going to tell you it's not the best reason. Now, it is a very good reason if it's man-made glass, but there's also naturally occurring glass. So this is the side of a volcanic mountain called Obsidian Dome. It's on the eastern side of the Sierras. That rock there is a really cool rock. Oh, I wish we had face-to-face lab, because I have samples of this. It has obsidian and pumice, which are two really cool rocks, kind of intertwined in one. I'll show you pictures of them eventually when we get to igneous rocks, but we should do a big field trip. Anyways, if you zoom in on that rock, you'll actually see it's made out of glass. So the point here is that humans aren't the only forces out there that can make glass. If you take magma in a volcano and you cool it so fast that there's no time for the atoms to make any fancy repeating pattern, then you've made a volcanic glass. So why is glass not a mineral? Well, the point of it being, whether or not it's man-made, that's not the main problem with glass. Because you can have naturally occurring glass, but even this naturally occurring glass is not a mineral. And here's the reason why. If you look at the glass, and let me hide my face because I'm blocking that view there. The problem with glass is that the atoms aren't arranged in an organized fashion. So when you take that liquefied quartz, that liquid SiO2, and you cool it super, super, super fast to make it a glass, there's no time for the atoms to arrange in a repeating pattern. So if you look at the black and white pictures, the little squares down here in the corner, quartz, which is this mineral over here, has this repeating pattern. The SiO2 is forming this beautiful lattice pattern. And that's in part what gives quartz the properties that it has. If you look at glass, it's made of the same ingredients, but they're not linked together in a particularly organized fashion. So if you kind of hear, it's just sort of this blob kind of a thing. So again, to be a mineral, you have to have not just a solid form, but the atoms inside of that need to be arranged in an organized fashion. In the case of glass, it's not organized. So I'm going to put this as number 4. Some textbooks, if you're reading the various versions of books I'm offering you, some actually combine it with solids. So the simpler, shorter way to be covering this is to say it has to be a crystalline solid. It has to be a solid with a crystal structure. I think that often doesn't mean that much to non-sciencey people. So I think separating it out and saying that the atoms inside the sample, inside the mineral, needs to be organized in this repeated pattern. I don't know if that's much better, but yeah. So the atoms must be arranged in an organized fashion. So the inside, well, I should say the atoms inside that sample must be arranged in an organized fashion. There needs to be this internal pattern. In the case of glass, there's no internal pattern. It just cooled too quickly for the atoms to get into any sort of organization. So minerals have to have a single chemical composition. It has to be solid. You can't manufacture it. And when it was turned into a solid, it had to happen slowly enough that the atoms could arrange themselves in this repeating pattern. If it cools so fast that there's not time for that, we get what we call glass. And glasses are not minerals. I mean, glasses are glass. There are some rocks that are made out of glass, but the main point for now is that it's not a mineral. So there's this company called LifeGem. If you're interested, and I'm not trying to market for them, but if you're interested, you can go to lifegem.com, written there on the screen. And what this company will do is it will take the ashes of a loved one, like maybe your pet poodle, and they will put it in a machine, and they will compress that carbon that's in the ashes of your loved one and turn it into a diamond. In fact, this diamond is no, okay, it's not. But anyways, on that lovely note, if you can make a diamond in the laboratory out of the ashes of your beloved pet poodle, should I be calling that a mineral? No. So, yeah, again, if you're making the mineral, well, if you're making the thing yourself, if it's man-made, yeah, nope, it should not be called a mineral. Okay, let's just talk a little bit more about graphite and diamond. So these are two minerals with two very different qualities to them. So presumably you're familiar with diamonds. It's a super, super hard mineral. It's transparent. It's sparkly. Do you guys know the other mineral that's up there? Have you guys seen the mineral graphite? I can almost guarantee you that you have. Now, you might be like, well, yeah, I've heard about like graphite as a lubricant. Okay, maybe you've heard of it that way, but I'm talking even more simplistically. If you've ever used a pencil for anything, and I'm sure you've had some Scantron thing where you've used a pencil, that pencil lead is not really lead because like kids chew on it and you don't want kids to be chewing on lead. So pencil lead is actually this mineral graphite. So this pencil lead is actually a mineral. It's this mineral called graphite. It has exactly the same chemical composition as diamonds. And yet it has very, very different properties, right? If you look at it, rather than being this transparent mineral, it looks like a metal. It's super metallic, it's super shiny looking, it's super soft, which is why it's such a good lubricant. It's also why it's good for writing with your pencil. Super, super soft mineral. I mean, it just looks super different. And yet, they have the same chemical composition. So I want to return to our requirements for something to be a mineral. Let's get it all there on that screen there. So we were just talking about, again, how you have to have a single chemical composition. And we talked about quartz and calcite as examples. It has to be solid. It must be naturally occurring. We'll get this. And the atoms need to be arranged in an organized fashion. And it's really the first one and the last one that really give a mineral the properties that it has. So I'm just going to kind of box this. Okay, you can figure out how you want to put that in your own notes. But these two things are the most important for giving a mineral its physical properties. So most important for giving minerals their physical properties. So in lab this week, you've been or you're getting introduced to the physical properties of minerals. Physical properties that minerals have, whether it looks like a metal, whether it looks like glass, whether it's hard, whether it's soft, is determined based on these two things, the chemical composition and how those atoms are arranged. And graphite and diamonds are just kind of fun examples. So I'm just going to write a little bit on the board about graphite and diamonds. I'm not going to test you like on graphite and diamond per se, but I want you to understand why they're significant. Okay, so graphite versus diamond. And again, you might want to add to your own notes that graphite is what we call pencil lead. So same stuff, something that's familiar to you. Graphite and diamond are made of exactly the same material. They're both made out of carbon. I could take the ashes of my loved one and I could either make a diamond or I could make graphite. I guess technically there would not be natural minerals since somebody's making them. But the point is that they're made of exactly the same chemical composition. So they both have a single chemical composition throughout. What's different about the two of these is how the atoms are arranged. In the example of graphite, the carbon atoms are arranged in one way, and in the case of diamond, they are arranged in a different way, and it's just the arrangement of the atoms that make these two minerals look so different. Makes one mineral super hard, transparent. The other one, it looks like a metal, it's slippery, it's super, super soft, very different physical properties just because of that crystalline structure. So let me just show you their crystalline structures. So again, it's only carbon. So all of the stuff is the same stuff. So the different balls are balls of carbon. In the picture to the left there's some red layers, some green layers, some blue layers. It's all carbon. So they're just using colors to help you see that in that example, the carbon atoms are forming these little hexagons that are linked together, forming these sheets. In the black and white picture, on the other side there, those carbon atoms are aligned in a much more complex fashion. There's more bonds going in very different directions. There's not like this nice layering pattern. So if you were to make a hypothesis, if you were to make an educated guess of which one would you guess is the diamond? Is the diamond the one forming those nice layers, or is diamond the more complex one on the other side? It's the more complex one. What makes diamond so hard is that there's not one nice direction that's easily broken. If we look at the other sample there, the red and green and blue layered sample, that's your graphite. The black dashed lines are these really, really weak bonds that connect one layer to the next layer. And because those bonds are so weak, when you put your pencil down on a piece of paper, that blue layer of carbon, that bottom layer, gets left behind. The bonds between it and the upper two layers breaks. And if you keep writing, then that green layer of carbon is left behind and the next set of bonds breaks. So because the example there on the left is growing into these sheets with weak bonds between the sheets, it's giving that mineral graphite that particular physical property where it's super soft, it forms these slippery layers, which is very different from the diamond there on the other side, where again those carbon atoms are linked together in a much more complex, more compact fashion, creating a much more durable mineral. Here's just a couple other examples. So if we look here at how, this is a different mineral, how the atoms are arranged into one another, notice they're connecting to each other, forming like little cubes. They're forming 90-degree angles. If we look at this sample over here, a mineral called calcite, can you see the shape? And maybe this sample here and that sample there, maybe that one there, is the best example to look at. So that's one option. Another mineral that this might be is this mineral halite. So if you look at halite here, notice it is not diamond shape. It's more at 90-degree angles. So what would be your hypothesis? Is the pictures on the bottom, and they're the same mineral. They're just two different textbooks renditions of those minerals. Am I looking at that more diamond-shaped mineral calcite? Or am I looking at the more square-shaped, cubic-shaped halite? Or halite, but halite's how it's usually pronounced. I'm looking at the halite. Yeah, there's a reason this mineral halite grows into these 90-degree angles. It's the way those atoms are linking together inside. If we look at this set of atomic arrangements here, notice here the ingredients are forming more of that diamond pattern. So this one is which mineral? The one on the left which is halite, or the one on the right, the one that is calcite? Calcite. So this shape and this shape are a lot more similar. So yeah, just the shape the minerals grow into, the shape the minerals break into, the physical properties they have are dependent on their chemistry. What are they made out of, and how are those ingredients linked together? The specifics of these minerals you're going to get in lab. You'll learn more about halite and calcite. But for right now, the general principle is to understand the importance of the crystalline structure. Okay, so the big principle, again, and we just keep sort of saying the same thing, but the physical properties that a mineral has is really due to the mineral's chemistry. So this is the reason why, if you want to become a geology major, you do need to take usually a year of chemistry. I think Sac State is working on reducing some of the math and chemistry requirements, but depending on what subfield of geology you want to go into, if you like mineralogy, if you want to understand minerals and what you can learn from minerals, it's really based a lot on chemistry. So I know some of you are like, no, but this is applied chemistry. So what I think a lot of people don't like about science classes is that you're like, why do I care? And the cool thing with geology is we're taking all that stuff from chemistry and physics and biology, and we're talking about why we care. Why do we learn about these things in physics and chemistry? Well, we can learn about the Earth. And the Earth is cool. Who would not want to learn about the Earth? Okay, so here's a pretty mineral right there. Let's put my face back on there. So again, it's got a certain sort of physical properties, and one of the physical properties that you were learning in lab earlier this week, hopefully, if you did that lab, was the crystal form of the mineral. Do you guys remember what the crystal form of a mineral is? It's the shape that a mineral naturally wants to grow into. So depending on how those atoms are arranged, it might grow into this shape. Lab today, or the second lab for this week, we will be looking at the cleavage, which is the shape that a mineral breaks into. And one of the challenges is, like, if you're looking at a sample, am I looking at the shape it's growing into? Or am I looking at the shape it has broken into? And there are signs we can look for, and the more geology you take, the better you get at being able to tell. Am I looking at a broken piece of a crystal, or is that the shape the crystal grew into? This one, I'm just telling you, is the shape that mineral or that crystal grew into. And we use mineral and crystal pretty interchangeably. So those of you that remember Monday's lab, or the lab 1 from this week, what do you say? What do you think? What is the crystal form? Do you remember the various options? I'm listening. Okay, it has a prismatic crystal form. So these things that look, I mean, it's sort of your standard quartz crystal, big, chunky, it's not flat. That is a prismatic crystal form. Okay, so here's another mineral showing its crystal form. This one here, I don't know how easily you can see, but it's not big and chunky. It's flat. And you almost kind of want to peel the various little layers off. And if you did, they'd be like flat pieces of paper. Do you guys remember the name of that crystal form? So tablet of paper, tabular. So this is a tabular crystal form, and that's kind of like that graphite where there are these layers and then there's these very weak bonds between them, which makes it kind of want to peel off into these layers, and it grows into layers. This crystal form right here, so they're a lot longer and they're flat. So if it was prismatic, it would be chunky. This is long and flat, almost like a butter knife. It looks kind of like a blade, so think long, flat. Opposed to the tabular, which are wider. So tabular is this wider sheet of paper thing. If I just have like a thin strip of paper, then I get that next one right there that kind of looks like knife blades, maybe a whole bunch of little knives sticking out of the rock there. So that's called bladed, if it looks like blades. There's a close-up of it. So like each individual piece would look kind of like a butter knife. So some minerals grow with a bladed crystal form. Ooh, what about that one? Let me get my head out of the way there. It kind of looks fuzzy, but if you touched it, it would be like a cactus. It's all spiky. Almost looks like a bunch of needles sticking out. Do you remember that one? So really skinny, needle-like, acicular. All right, so yeah, that's actually a pile of needles. So if it looks like a pile of needles, it is acicular. That one's kind of a fuzzy one right there. This one, if you take it, it kind of disintegrates into powder, almost like you have got a really worn pair of jeans and you kind of get that little fuzz there at the knee or in the pockets maybe. So this one, do you remember what that one is? It looks kind of like fiber. Hint, hint, nudge, nudge. That one is fibrous. This is the mineral asbestos. By the way, the California state rock, and yes, we have a California state rock. It's called serpentine. And one of the main minerals that we find in this rock is asbestos. There's actually a lot of controversy in the past about should we determine a new state rock because we don't want the state rock to have asbestos in it. Somebody must have taken a geology class and heard their teacher like, yeah, the state rock has asbestos in it. It's true. Okay, what crystal form does this one have? So it's not, I mean, it's chunky, but it's not like long and chunky like the prismatic one was. This is growing into little squares, little cubes. So if it looks like cubes, little squares, we call that crystal form equant. It's equal in length in all directions. It has an equant crystal form. Okay, let's see, other things from lab earlier this week. Can I test to make sure that this ring is diamond by seeing if it scratches glass? Like there's hey, if it scratches glass, it must be diamond. Well, will diamonds scratch glass? So this is where we were talking about the hardness, how you determine the hardness of one thing compared to another. Do you remember the hardness of glass from lab? It's 5.5 on Mohs hardness scale, where again, 1 is soft, 10 is the hardest. Do you know the hardness of diamond? 10. So yeah, so diamond has a really hard hardness. So should it scratch glass? Yeah, it definitely does scratch glass. Is it the only mineral that scratches glass? Well, actually, glass really isn't that hard. If glass has a hardness of 5.5, that's like halfway through the scale. Quartz has a hardness of 7. Would quartz scratch glass? Yeah, if quartz, since it's a bigger number than 5.5, this would scratch glass. So I could take this, look at my diamond ring, I can prove it's diamond, it scratches glass. Okay, so just because something scratches glass doesn't mean it has to be a diamond. Bigger principle, though, is you can determine the comparable or the relative hardnesses by scratching one thing against another. If it leaves a gouge in that other thing, it must be harder than that thing, right? If this mineral scratches my arm, I'm not going to actually do that, but if the mineral scratches my arm, it must be harder than my arm. Okay. Other things reviewing, let's see here, how are these physical properties varying? Like, what do you see is different? Kind of, I don't know, maybe you see different things than me, but there's like, to me, one especially dramatic difference between these. I would answer their color. So color was another physical property of minerals, and again, it depends on the chemistry inside. So the real reason I wanted to put up this picture right here is really two reasons. Number one, is there like fancy terminology we use for color? No. So clear, or you could say whitish, or you could be like purple or orange-ish. I always like adding ish because it's kind of orange. Brownish, blackish, grayish, pink. Interestingly, all of these minerals started out as quartz. So one of the secondary point to color is people love color. They're like, this mineral is yellow. I know what it is. This mineral is purple. I know what it is. Well, it turns out color is super unreliable. And the reason for that is even though we say minerals have to have a single chemical composition throughout, we recognize that occasionally there'll be impurities in the sample. And if you get a little impurity, that mineral won't be that beautiful transparent quartz. It'll turn into one of these other versions of quartz. So this is the normal classic chemical formula for quartz. If a little bit of iron, and it's a particular variety of iron, iron with +3 electrical charge, if that iron makes its way into the crystal structure, it turns it purple. And that's what amethyst is. So amethyst is actually just quartz. I should wait. The next slide, we'll get into what I wanted to talk about. But yeah, a small impurity can change the color. Here's another variety of iron. If that variety of iron gets into the sample, it turns it like yellowish orange. And that's a less commonly known variety of quartz called citrine. If aluminum gets into the crystal structure, it will turn it kind of blackish gray, and that will be smoky quartz. And if there's a combination of aluminum and phosphorus that make its way into the crystal structure, you get rose quartz. So you can't just say quartz is white, because if there's a little impurity, it can really mess things up. So for a more reliable sense of a mineral's color, is we determine what we see on this slide. I was hoping it didn't give you the answer, but it did, so I'll just run with it. The streak. So remember, the streak is the color of the powdered mineral. And this is where it is fun to just get to do this yourself, but I get that, we're online. But if you happen to have a mineral and you happen to have, we say unglazed porcelain, it's just because that streak plate is hard. Find something hard. Find a piece of tile somewhere. If you can rub the mineral against the tile, you're going to break it apart, and it's going to show the true color of the mineral. And most of the time, the streak color is the same as the mineral color. You break down a white thing, it creates a white powder. You break down a yellow thing, it creates a yellow powder. But part of what's really cool is when it doesn't. So that mineral there is very silvery, sparkly looking. And when you rub it against the streak plate, it creates this like brick red maroon powder, which is like, wow. So like deep inside, that was the color it wanted to be. And in fact, if we go back to our quartz examples over here, if I take any of these varieties of quartz, I could take the amethyst, the citrine, the smoky quartz, the rose quartz. If I were to break them into a powder, they would all have exactly the same color powder. They all create white powder. Because most of its inherent nature is that root variety of quartz, which is white, this kind of one over here. So even though the small impurities are making our eyes see colors like purple and orange and gray and pink, in reality, when you crush it and you just have little bits of powder, it actually has a white streak. So that's why we talk about a streak. It's just more reliable to talk about that than to actually look at the true mineral's color. Do you guys remember how hard a streak plate is? These are just things you just need to know for the mineral exam. It's 6.5. Is the hardness of it. Will diamond leave a streak on a streak plate? No, diamonds are harder than 6.5. If I rub a diamond against the streak plate, I'm going to make a gouge in the streak plate. So you can't always determine a mineral streak because you can't always make a powder of it. But if you can, then we just assess its color and call that the streak. Given time, I'm going to maybe come back to those a little bit later on. In the lab for day 2 of this week, you also are getting introduced to this quality called the luster, which is the quality of light reflecting off of a mineral, which I always thought was a weird definition. But if you take these two minerals, they're both kind of like yellowish, goldish, orangish. Okay, they're not exactly the same color, but the point here is that you can have two things that are basically the same color, and one can be very dull looking, I guess this one's the dull looking one, and one can be very shiny, like a mineral. So if you're looking at how shiny a mineral is, and even more specifically, does it look like a hunk of metal, or does it not look like a hunk of metal? If it looks like a hunk of metal, or like that silvery one, then we say it has a metallic luster. It shines like a metal. If it does not, where is it? That one over there. If it does not shine like a metal, then we say it has a non-metallic luster. And in lab, you'll be introduced to other varieties of luster. This one has an earthy luster. It looks like dirt. Another property that is super fun is There are some minerals where if you drop acid on it, it'll bubble, which is always just really fun to do. The same mineral also is prone to what we call double refraction. You put it on some text and you look through it and you get a double image. And actually people have talked about trying to use that quality to create like a cloaking device to like hide that Klingon warship. And you're like, what? How does that work? Oh, there's my Klingon thing. It was supposed to appear. I don't know. Oh, there it is. Oh, it's because the calcite was hiding it. So this is actually what some scientists have actually created. So there's this red bar going through, and here's the mineral calcite, and they kind of put it at just the right angle that it's bending the light in such a way that the red bar basically disappears. Okay, you can kind of see it, but it's pretty invisible, and if you're out there in space, you might not see it. Here's another example of it where they have the pattern background to kind of help you see the difference. So here you see the red bar, right where the calcite is, it disappears. And what they're doing is they're taking advantage of refraction. So this is the university in China that's doing it. This is my Harry Potter reference. Maybe his cloak was made out of calcite. But basically, as the light travels, if it refracts, if it bends and you kind of bend it, you can have that light pass around that bar, that hidden object, so that it hides the object. And this is actually the image of it. So that bar that went all the way through, it pretty much disappears underneath. So it's something they're working on, like trying to make things invisible by taking advantage of this physical property of this mineral. Okay, I've run over, so we should just leave it. I do have another more specific video just related to physical properties of minerals, and we will talk more about mineral stuff next time.